Good day and welcome back for part 3 of our introduction into the double integral. So recall in the previous videos we've seen that a double integral is calculating an enclosed volume. And to be even more technical, we could say a net difference of enclosed volumes. So with this in mind, I want to start off with a slightly different example than we have previously encountered. For the rectangle 0 to 1 times 0 to 1, remember the first interval is telling us how the x values vary, the second is telling us how the y values vary. We would like to evaluate this double integral. And pay particular attention to this word evaluate. Our previous example, we approximate it, but we certainly did not evaluate. That is, we want to know exactly what is the value of this double integral. And the only way we can do this exactly at this point is through a geometric interpretation. So that is indicating to us that we need to sketch the graph. So interpret geometrically. And whenever we see that language to interpret it geometrically, that's going to be through drawing some picture representing the surface. So in this case, we have 0, 1 times 0, 1. So we really only need the first octant. So we're looking x, y, z. And I would like to try to get a rough idea of what the graph of this surface would look like. So I'm thinking z equals 4 minus 2y. What word would you use to describe this surface? And hopefully you said the right word here, not a line, but this is a plane. But we could really think of it in terms of a line if we look at a specific trace. So if you were to look at the x equals 0 trace, i.e. flat in your screen, we would have a line which has a z-intercept 4 and it has a y-intercept 2. So roughly speaking, the x equals 0 trace would be something of the form given here. And remember, because that x variable is not present, every single x equals trace is exactly the same. So to get an idea of what this plane looks like, we would simply take this line and we would drag it along that x-axis. And so that gives us a rough idea of what our plane, z equals 4 minus 2y, will look like. And what we need to focus in on is what portion of this plane is sitting above the rectangle R. That is what we are interested in. So R is described as being a rectangle going from 0 to 1 in the x direction, 0 to 1 in the y direction. So we will start at kind of each corner of this rectangle and just trace up to where we hit the plane. So starting on the x-axis, we would go all the way up to z equals 4. On the y-axis, we would trace up to where we hit that plane. And then similarly, at that corner point, we would also go to where we hit the plane. So tracing over on the plane now, the top part of our surface, we have something that I would very technically describe as looking like half a house. And just to make sure that we're keeping our goal in sight, this double integral, whose value we are going to determine precisely, is going to be the enclosed volume that we see to the left. And to calculate this enclosed volume, I'm going to simply break that solid up into two parts. There's kind of the top part and the bottom part. And I'm going to think about labeling the lengths of each side. So in terms of the bottom, we have a square with side length 1. And in terms of getting up to the plane, we have a height 2. So the first base portion of this solid has a volume which is given by 1 times 1 times 2. So it's simply the volume of a box, which is the ideal scenario. Now for the second part, we might describe this as being kind of a triangular prism, which is essentially indicating that we have this triangular end cap, and we are simply giving it some depth. So if we'd like to find the volume of this top portion, we would take the area of the end cap and then multiply it by how long it is. So note, this would be 1 unit in depth. and then 1 and 2. So the area of that triangular end cap is 1/2 times 1 times 2. So this would be the area of the triangle, and we're multiplying this by how long it is or how much depth it has, which is 1. So we end up with 2 plus 1, or the exact value of this double integral is 3. And before moving on, it's worth noting that at this point in time, we are only able to evaluate a double integral exactly if we can interpret it from this geometric perspective, which is a very important and powerful tool to keep in mind. Now, let's finish with a few basic properties of the double integral. And these should all look kind of familiar from our previous experience, but just suitably rephrased for functions of several variables. So if you wanted to evaluate a double integral of a function plus a function, it is very reasonable that you would break the double integral into the function of integral of the first plus the integral of the second. And we can do this just as easily with a minus as we can with a plus. Similarly, if you have a constant inside a double integral, you can pull that out front as long as it's multiplied by each and every term inside. That is, this is the constant times the double integral over r. And before stating this last property, which is going to be a useful thing to keep in mind for future discussions, let me note the Calc 1 version of this. If I wanted to integrate from a to b the function 1, one way you could go about this is you could just interpret what's going on geometrically. You have the interval from a to b, and if you look at the curve given by y equals 1, you know, how much area is enclosed below that curve and above the x-axis. And we would note it's a rectangle, so you would take its height 1 multiplied by its length, b minus a. And I'm going to write this as the length of the interval from a to b. And we typically would not have made this observation back when we were in Calculus 1, as there was probably no need to do so. But kind of laying the groundwork for what's to come, and that would be double integrals over general regions and eventually even triple integrals. So lots of fun and exciting things to look forward to. That if we are evaluating the double integral over some, I'll just say region, so at this point in time it's a rectangle, of the function 1, our analogous version of the Calculus 1 property is that what we will get back is the area of that region, R. So this completes our introduction into the double integral. In the next few videos related to this current section, we're going to look at how we can go about using techniques of integration to evaluate. So stay tuned and take care.